So, hello everybody. In this section, we are going to take a look at this question with the 35th problem in Project Euler, which is this circular prime. So, okay, yes, circular primes. The number 197 is called as a circular prime. In this section, we are going to take a look because all rotations of the digits are 197, 971, and 719 are themselves prime. So, which means that we rotate the digits and you'll find whether after rotation the number is prime or not. So, there are 13 such primes below 100, 2, 5, 2, 3, 5, 7, 11, 13, 17, 21, 37, 71, 73, and so on. So how many circular primes are there below 1 million? So basically, the operations that we are going to do in this question is just basically extracting the first digit from the number and add the digits to the last of the number. So let's say for 197, we extract 1 out. So our number left 97. So the rotation means we add the 1 here. So how can we do that? Basically we move away this one by mathematical operation. So how do we do that? So ever heard of logarithm? So for logarithm, basically we are trying to find how many power for a number such that it satisfies the value for the value like this. So let's say if we put it right, what is the power for 2 to become 8? So we use something like this. Okay. So this is easy because the number is small. So when the number is big or the number is something like 6, then the n numbers here will not be able to can be found in such a simple way. So this is where logarithm becomes useful here. So let's say we have 6, right? So we add log 10, 2 power n equals to log 6. We add log 10 to both sides. So it doesn't matter which log you use. You can use log base 2 or log base 8, or as long as the value from you both sides are the same. If you add log base 8 to the left side, then you should add log base 8 to the right side to maintain the value from both sides. So for convenience, I just use log 10. So there's a law in logarithm, which is log base AB power n can be expressed in log AB. So by using this formula, we can do something like this. So the value for n can be found very easily by using log. So that's it. So this is the value for n. So why is this so useful in this situation because when I use log 10, I can find the number of digits in the number, because from log 10 1 equals to 0, log 10 10 equals to 1, log 10 1 equals to 2, log 10 1000 equals to 3, log 10 equals to 4. So it's basically very simple here, because you can do something like this and you will get 2 log 10 10. So this is equal to 2, because there is another theory that says log n equals to 1. So yeah, that's pretty simple here. So now you can see from here, 10 is 2 digits, 100 is 3 digits, 1000 is 4 digits. So in order to get the number of digits in the number, we can just add 1 to the result for log 10 of that number. So this will allow us to get the number of digits in the for certain number. So next, let's say 190. Let's say, okay, for this question, for this number, if we use log 10 on this number, the value would be ranged between 2 to 3, as you can see from this table. But in fact, to get a number digit, as I said earlier, you have to plus 1. So we just add 1. So from here we know the number is somewhere between 3 and 4 for the log 10 value for this number. So to get the number of digits, we just change the double to integer, because it ranges on something close to 4, because it approaches 1000. If it is near to 100, then it will be 3 point something, maybe 3.0 something. Yeah. So by changing the number from double to integer, we get the number of digits. From here, then we can create a divisor to divide this number in order to extract this digit away. So from here, we should just put 10 power of 3, which is 1000. 10 power of 3, 1000. But the problem here is because log 10 and 10 power of something are basically under the same system. So instead of adding 1 to know the digit, we can just reuse the value here, 100. So we just change the value from log 10 of base 10 of the number. We get the value, then we convert the double value into integer value, and then we use it to construct a 10 power of that number in order to extract the first number from the first digit from the number. So after that, what we got is 9. So by using this 9, we already extract the last digit. So okay, so now we have to rotate the digits, which means that we have to move the 7 1 in front. So we can just use the remainder for 100. Goes to 71, and then we times it by 10. So, and now we can add with the digit, the first digit that we have extracted earlier. So now, yes, so it is 719. So if you do the same operation again, then you will get this again. So this is basically how we do the rotation operation on the number. So I can, if I want to formalize it, then I would use first equals to first divisor. We make the divisor first. So this is, so we put the log 10 value here. Log 10. So basically the formula is like this. So after knowing this operation, the problem can be solved easily. So let's see the code here. So first we do this Sifos-Iran-Totinis operations in order to find the prime numbers. So the question asks for prime numbers below 1 million, so we don't have to check arbitrarily, you just check until 1 million. So what is about this operation? Because as you know, checking prime number is slow, so I put this function in order to fasten up the operations a lot. So basically the function is like this, 2, 3, 4. Okay, we know that 0 and 1 are not prime numbers, so we skip them. So these are not prime number, and 2 is a prime number, so we start with 2. And next we mark the number that is a multiplier of 2 as not prime number because they can be divided by 2. So the example here are 4, 6, 8, and so what we left here are not divisible by 2. So for 3, we remove the multiplier of 3. So there are 6, 9, 6 we remove earlier because 2 times 3 equals to 6. So 9 here and 15 and 21, 27. So for now 4. Because 4 is not a prime number, then we don't care about it because the multiplier of 4 can be divided by 2. So next 5. 5. The multipliers are 10. 10 because it is divisible by 2, so we have removed it earlier. So next it is 15. 15 because 15 is divisible by 3, so we have removed it earlier. So now next 20. 20 is divisible by 2 again. So in this list we left 25. So we just remove 25, and for 7 and it should be 6 here, but 6 is removed, so we don't care about it because the multipliers of 6 can be divided by 2 again. And 7 is a prime number, so we check again. So this operation, for this operation we will do continuously until the square root of the number, the total number that we want to find. So the code is here. Okay, after finding the prime numbers, we can add all the prime numbers into an array so that we can use a prime number to check for the condition that meets this operation, this solution circular prime. Okay, so now prime number, so we start checking with the prime number. Circular primes. So the circular prime function is basically doing the same operation that I have explained in the earlier of this video. But there's a problem that you need to consider, because if you rotate into this form and you rotate again, that will be 3 numbers, and after that since you iterate from the small number to the bigger number, so eventually you encounter this, and you rotate this will be rotated again, and you get the same condition that satisfies this question. So eventually you'll get 3 overlapping solutions. So I put a flag here to check whether the number has been checked or not. If it has been checked, then we will skip it later. So it will speed up the things quite a bit. So this is a prime checking function. So, and that's it about this question. Next 55, which is the same with the official answer. So yes, that's all for this video. So we are hoping to see you next time. Thank you. Bye bye.